Today we're going to finish section 3.5. We'd started before, multiplication and division algorithms. We've gotten to the point where we had looked at all the multiplication algorithms and we had one more division algorithm to go. And we did the standard division algorithm, and the one that we are on now is called repeated subtraction. So the idea with repeated subtraction is that it's appealing to students who maybe have difficulty with multiplication tables, that kind of stuff. It is not a terribly efficient way of doing division. Let me take a look with you and you can see how this works. We're going to take our number 623 and basically we're going to subtract values of 5 times bases, the place value systems of our base. Speak right. So like 5 times 100. Technically you could do 5 times 1,000. That's bigger than our number this time around. But so you're subtracting or 5 times 10 or 5 times 1. The only thing you can subtract are 5 times a power of 10. So in this case, something like 5,000, 500, 55. So the only thing we subtract are these 5s. So taking a look back over at our number, the biggest one of these kinds of values we can subtract is actually 500. Now as we're doing this, we want to keep in mind what we've actually subtracted. We've actually subtracted 5 times 100. And we're going to use that information in a little bit. But as we go, we're going to subtract this. This is 123. Clearly I can't subtract 500 again, but I can subtract 50. And of course 50 is 5 times 10. If I subtract this, this gives me 73. Still big enough to subtract another 50, which is a 5 times 10. Okay, again, that gives me 23. And then I can subtract values of 5s, so because 50 is too big again. So this is 5 times 1, which is 18. And then we're going to subtract another 5 from 5 times 1, which gives me 13. We'll run out a little bit of space here on your paper. Hopefully you've got a little bit more space. If not, when you do the problems you will. So 13 minus another 5, which is the 5 times 1. That would be 8. One more 5, 5 times 1 gives me 3. Of course 3 is too small to actually subtract, so this is my remainder. That's the R3 value. So my answer then, what is my answer? Well, my answer is how many times I've multiplied by 5. So here's 100, 20, and then 1, 2, 3, 4. So this is 124 with a remainder of 3. And I can't remember if I have an example or if you have an example in your homework, but this will actually prove to be quite helpful for you when you're doing subtraction or division in other bases, because you don't know your multiplication tables in base 3 or base 7, right? You only know your multiplication tables in base 10. So if you're having difficulty, or if you have students with difficulty where they're remembering multiplication tables, repeated subtraction gives an alternate algorithm that helps with that. All right, we're going to switch gears just a little bit, but from talking about algorithms, and we're going to do, I think we have 3 or 4 examples of multiplication, division problems in action. So these are like application problems, and when we see the multiplication or division inside of there, we are going to show the multiplication or the division. So this is not, use your calculator time. That kind of defeats the whole point of this section if you're using your calculator. So when you do each step, try to think, what kind of multiplication algorithm or division algorithm could I use? Please don't always use standard, because there are going to be places on your test where I'm very specifically going to say, use the lattice algorithm. And if you haven't practiced it a fair bit, then it might be difficult to do. So let's take a look. We have Juan, and he saved $5,340 in 3 years. It says he saved the $95 per month the first year, and then we don't know how much he saved per month the next couple of years, but it's the same amount every month. How much did he save per month the last 2 years? So the first thing we'd like to figure out is how much he saved in the first year. It says he saved $95 per month. So this is like 95 times 12. So we have this multiplication problem. We can use any of the methods of multiplication we'd like. I think I'll use partial products on this one. So partial products, remember, is where I split up the 90 and the 5 and the 12 as 10 and 2. And we make a box. And inside of each of the corners of the box, we're going to actually do the multiplication. So 90 times 10 is 900. 5 times 10 is 50. 90 times 2 would be 180. And then 5 times 2 is 10. So then we're going to add these together. 900 plus 180 plus 50 plus 10. I tend to go smallest to largest in that, or I said that wrong. Largest down to smallest in that. When I do that addition, there's absolutely nothing special about that. So you certainly don't need to do that. We're going to add up the right column first. I'm going to go ahead and use the standard algorithm. Actually, you know what? This is enough numbers. Let me use scratch addition, just for fun. All right, so we have the zeros all together. So that's, of course, 0. With scratch addition, remember we have 8 plus 5, that's 13. I'm going to scratch and remember a 3. I have 3 plus 1 is 4. So this is the number 4. And then I had 1 scratch, so I do 1 carry. I have 1 plus 9, that's 10, so I'll scratch. It leaves me with 0, plus 1 is 1. So it leaves me with 1. I scratched 1. So I'm going to have that 1 at the beginning, so this is 1140. So in the first year, it was 12 months, the first year of this savings plan, one saved $1,140 or $1,140. So overall, though, he saved $5,000 something. So during the first year, he did not save, like a third of the amount. So let's figure out how much more he saved in the last 2 years. So this is 5,340 minus his 1140. This is actually a really nice one. We could do left to right addition if we wanted to. 5 minus 1, that's 5,000 minus 1,000 would be 4,000. 3 minus 1, 3 would be, you know what, I'm not sure this is the best choice in this one. Let me back up. Let's just use our standard algorithm for this one for now. All right, so we'll do 0 over here. There's no borrowing anyway, so in that sense, it's kind of nice. 4 minus 4 is 0. 3 minus 1 is 2. And 5 minus 1 is 4. So we have $4,200 left that he saved. And this is in the course of the last 2 years. And of course, the thing we need to remember is that 2 years is equivalent to 24 months. Because the question, remember, asked us something about how much he saved per month. All right, so we have $4,200 saved, and it's saved in 24 months. And so if we want to know how much is saved per month, this would be division by 24. All right, let's try that as a repeated subtraction algorithm because we feel like it's maybe a little bit awkward, I think, and I do feel like it's awkward as well. This is not going to be an efficient way to do this problem just because I know what the answer ends up being, but I want you to see how it would work if you weren't knowing how to do this. And in particular, it has appeal because you don't know a multiplication tables for 24. And so you're always doing sort of an approximate of how many times does 2 go into 4, but it doesn't always work exactly because it's not really 20, it's 24 and that kind of stuff. So let me show you this. This would be 24. So 24 hundreds is actually what's here. So it's 24 times 100. And then when I subtract, I get 1,800 here. All right. I can't take another away another 2,400, but I can take away another 240. And this is when this problem is going to become long. It will, because we're going to take away 240 several times. All right, so when we take this away, I get 6, 5, 1560. We'll do 240 again. That's a 2, a 3, 1320. We'll do 240 again. It's 1080. I'm doing this subtraction sort of in my head as I go. Of course, if your students are still working or concerned about the working with the subtraction, you'd want to show more detail. But we're going to presume if we're working on multiplication, that's going to be somewhere along the lines of end of second grade, beginning of third grade. Especially this kind of a multiplication where we're dividing by 24, or division where we're dividing by 24. That's going to be a third grade, maybe even early fourth grade topic. So the addition and subtraction hopefully should be down by then, and that's not that big of a deal since that's a first, second grade topic. All right, so 8 minus 4, and then I have 10 minus 2. Okay, we'll do another 240 over here. All right, we're getting close. We got 600. right, let me move a little bit of my work around so that I have some more space. Okay, I think that worked pretty well. It doesn't look especially nice when I'm done, I guess. Let me kind of do this. That might be a little bit helpful. Yeah, this is not the kind of work I'd want to see in your paper, of course. I'm running out of space, of course, and you guys know that. So just be a little bit clearer in yours, and you've got more space to keep working down. And you know what? If you kill a few trees on this particular assignment, then I think we'll still be okay. All right, so this is 24 times 10 again. This is 0, a 6. 6 would become a 5, 5, 4, 3. Oh, we're so close, 240. 24 times another 10. All right, 120. So that's too small now to subtract another 240. But of course, we can still subtract a 24, and we will do so several times. So this is 24 times 1 now. 6, and then I've got 11 to 9. Another 24. We're getting ever so close. 2 here is 7 here. We should have about 3 more subtractions. This is an 8. I didn't do that. Yeah, it was an 8, that's right. It's a 4, that's what's wrong here. Okay, good. And then we'll do another 24 here. And our very last 24 subtraction, which gives me 0, of course, in here. All right, let's count up what in the world we got as an answer. So this is 100, and then I've got 10, 20, 30, 40, 50, 60. Oh, I think I missed one right here. Over here. I did. Let me write it in. That one was there. And I missed writing one down. I was like, I thought I had 70 of them. There we go. There's another one I missed. So be careful on writing those. Don't miss it like I did. Well, let's count them again. I have 120, 10, 20, 30, 40, 50, 60, 70. So that's 170 so far. 170. And then I have 1, 2, 3, 4, 5. So this is 175. So one saved $175 per month. And of course, like I said, the repeated subtraction is not terribly efficient. You don't have to do, the non-standard algorithms everywhere. I do want you to practice some of them, though. So this will be an example of one. All right, let's take a look at the next one. Dan. Dan has 4,520 pennies and 3 boxes. So all of a sudden I see something about boxes, and I am just naturally led to drawing me 3 boxes so that I can discuss this in a moment. He says there are 3 times as many pennies in the first box as in the third, and there are twice as many in the second as the first. How much money does he have in each box? So all of this is hinging back on the very third box, actually, which says X. It says the first box has 3 times that, so we'll call that 3X. And that the middle box has twice as much as the first, so we have twice as much as 3X, right? Which looks an awful lot like 6X, of course. All right, so what we know is that all of these pennies add up, and they give us 4,520 pennies in the 3 boxes. So we're going to take all of this and we're going to combine it. So we're going to take the 3X, the 6X, and the X, and that adds to 4,520. 6, 7, now this is 10 X's on the left, equal to 4,520. Dividing by 10 is ever so nice because division by 10 actually removes zeros. So this is actually 452. The division for that's not terribly exciting if I show the step because it's division by 10. But. All right, so this is 452. So what is that telling me? Well, it tells me that there's 452 pennies in the last box. Each of the other 2 boxes would be multiplication, so this would be 3 times 452, which gives me 1,356. And then in the middle box, I need 6 times 452. Or you could just take the 1356 and double it. That would be okay as well. And you're going to get 2,712. Now we have to be careful, though, because we want to answer the question asked, which is how much money does he have in each box? So these answers are how many pennies he has in each box, but not how much money. So if I have a box with 1,356 pennies, this is actually $13.56. That's actually answering the question that was posed. Box 2, where I have 2,712, would be $27.12. And box 3, where I have 452, would be $4.52. Please, please, please make sure you answer the question that's asked in the way that it's being asked. All right, number 9. This is an interesting one. A student observes that 39 plus 41 equals 40 plus 40, and asks if 39 times 41 equals 40 times 40. And the question is, how do you respond? So this is a very simple question of, does this work? It doesn't even have to go into detail any further of why or why not. So let's take a look at 39 times 41 and 40 times 40. Now the 40 times 40 you can do very quickly without any algorithms per se, because 4 times 4 is 16, and then I've got the 2 zeros. The 39 times 41, let's try that one with lattice. I haven't done one of those on this video. So we're going to do 3, 9, 4, and 1. And we're going to draw the lattice. Okay, so if you remember, the way lattice works is we make the grid just like I did on the partial products. And the part that's different is that I split each of my boxes into 2 pieces. And then I'm going to do my multiplication. So 3 times 4 is 12. 9 times 4 is 36. 3 times 1 is 3, and 9 times 1 is 9. And then I expand along my diagonals. So in the bottom right-hand corner, I have a 9. Then I have 6 plus 3, which is 9. 3 plus 2, which is 5. And then 1 here on top. So I get 15.99. And of course, if we compare these, they're not equal. Now what we're going to find out is we're going to find out on the next problem that there is a pattern for that actually happening. So let's take a look at that one. So the answer right now, I haven't written it down yet, again, just like I told you a minute ago, make sure you answer the question, is that no, it doesn't work. And the answer is because the $15.99 that we just got does not equal 1,600. And it's as simple as that. The 2 values just don't work. Okay, let's look at the pattern of what's going on there in a little bit different way, though, asking the question somewhat different. So the first student, they said this argument there asked this question. So another student observes that when you do the 39 times 41, it looks like it's almost 40 plus 40. They're awfully close, but it's just off by 1. And then so he tries it again, another number. He says, okay, well, let's try the 49 times 51. And he notices that it's also 50 times 50 minus 1. So he wants to know if the pattern continues. If it does, what does the relation have to be between the first 2 values in the equation? So, interesting question. One of the things that we would notice right now quickly is that the pattern that the student is using is that the 2 numbers are 1 apart. I'm sorry, not 1, I shouldn't say it that way. They're 2 apart. So when you compare 39 and 41 or 49 and 50, there's exactly 1 number in between it, right? So there is a relationship there that is important to realize. So when we talk about a pattern, that's the first thing that we're noticing. So if we were to try this, we would be talking about, I'm going to do this a general argument, and to consider this. So we're going to consider having one value and the other value would be exactly 2 bigger than the first one, right? 39 plus 2 is 41. 49 plus 2 is 51. All right, if we multiply this, taking a look at just what we're getting in terms of some algebra, we have x squared plus 2x. Okay, now notice how that relates to the right-hand side. So this is the left side that we were working with on both of their equations that they created. Let's take a look at the right-hand side. And the right-hand side, notice, is the number that's in between the x and the x plus 2. Well, in between x and x plus 2 is x plus 1. So we're going to do x plus 1 squared. So it's x plus 1 times x plus 1. And I want to notice that when I do this, it should be exactly 1 bigger than the one before. So let's take a look. So you know from multiplication with distribution that you'd have x squared when you multiply the first two terms together. And then just like we have done before too, we have our inside and our outside terms. So I have x plus x, which is 2x. And then finally I have my last term is 1 times 1, which is 1. And of course you notice that they both have the x squared. They both have a 2x. The only thing different is the plus 1 at the end. All right, so this always works. Yes, so this will work anytime the values are 2 apart. Now here's a tricky thing to realize. Well, two things. First, what that means is it doesn't have to be 39, 41, 49, 51, 69, 71, something like that. It can be any two numbers, so it could be 33 and 35. It could be 12 and 14. It could be 132 and 134. So it's any two numbers that are actually 2 apart. Now notice, or you might ask yourself, well, is there something special about the 2 apart? Could I have them say 6 apart and split the difference halfway? And the answer is you could, but it wouldn't be only one more. There would be another factor at the end, and you could figure it out in the same way. Now this question is not exactly posing that, but it could be phrased just slightly differently, and it would. So like, let's say that the numbers were 6 apart. You'd have to look at what this value looks like, and you'd have to compare it to the value that's halfway in between, which would be x plus 3 times x plus 3. And they wouldn't just be 1 apart, right? They would actually end up being, if I'm looking at this correctly, just off the top of my head, I think they would end up being 3 apart. And there might be a relationship or a pattern as well if I start to think about it a little bit further of how far apart they are based on how far apart the original numbers are too. So some really interesting sort of number theory kinds of arguments with this. All right, we're going to switch gears one more time. We're going to take a look at some mental mathematics now, and then we've got some computational estimation to follow up with after that. Just like when we were doing mental mathematics in the last section, I know the whole point is that it's supposed to be in your head, but since I can't see that, we're going to write down a little bit of what's in our head going on to justify what we're thinking. All right, so the first one is called front-end multiplication. And front-end multiplication is like the front-end addition. You're just multiplying the first value first. So this is like 40, and we're going to do it 40 times my 5, so that gives me 200. And then we're going to do the 6 times the 5, which gives me 30, and we're going to add our result to give us 230. So this works nicely when you're multiplying one of the values as a single digit, like this is a single digit. It also basically is just doing the multiplication where you're starting with the left to right. So you could also kind of talk about it that way. All right, and I should make mention too, there's nothing special about the fact that it's 46, as in it's a 2-digit number. You could do it with a 3-digit number or 4-digit number. But generally speaking, this works best when you're multiplying one of the factors is a 1-digit number. All right, compatible numbers. We talked about compatible numbers with addition before. Things that add to 10 basically, or 100 make things compatible. So we're going to do the same kind of thing here, but it's with multiplication. So things that multiply to being something that's a power of 10 or a multiple of 10 are often helpful. So for example, I do not want to multiply 4 times 8. That is not helpful. It gives me 32, and I don't know about you, but multiplying 32 by something else after that is not going to be especially mental for me. I'd like to multiply something different, though, together. For example, maybe we decide we're going to multiply the 4 times the 5. Now, that actually would be pretty helpful because the 4 times the 5 is a multiple of 10. It's 20, right? And while we could group the 8 with something, and that would be fine, I kind of like the 5 and the 2 together at the end a little bit better because that's a 10. And then, of course, I still have my 8. So I'm gonna multiply from left to right. 20 times 10, that's 200. And then we've got 200 times 8, and so then I have 1600. Okay, so let's say you didn't actually think, oh, I'm going to multiply the 4 times the 5. You started with an 8 times 5. That's okay. That's going to give you 40, and then you're going to have a 40 times 4. So you're going to get 160 times the other 10 would be 1600. So the order isn't so important. It's just to notice what's compatible. That is, what kind of numbers multiply into being something nice and clean and easy to work with, which usually means that they have a 0 in their ones place when you multiply them. Possibly even a 0 in the twos and the tens place if you have bigger numbers. All right, thinking money. This is one of the ones that students often just overlook when they're seeing it because I'm not really sure why the because is. I guess probably because you don't actually see decimal places and dollar signs. But thinking money is extremely helpful. So let's take a look at the 46 times 5. If we think of 5 as a nickel, then we could say that this is actually saying I have 46 nickels. I don't want 46 nickels. That's a lot of coins. So let's say that instead of having 46 nickels, how many would I have if it were in dimes? Well, I'd have half as many. So instead of 46 nickels, I'd have 23 dimes. Now, the reason that this is working is basically because you're multiplying this one by 2 and you're dividing this one by 2. So it's kind of like the trading off algorithms we had for addition before. But thinking about it in terms of money, we don't even think about the fact that we're doing that. We just do it. And this is nice. Turning things into dimes is very, very nice because then I actually have a 10 in there. And 23 times 10, of course, is 230. So the multiplication for it just works out so cleanly because we thought of it in terms of money. Now, we can do the same thing on this one, but it's, of course, a 25. That's not a nickel. So a 25 is, of course, a quarter. All right, so if I have 44 quarters, what does that look like? Well, I have 44 times 25, so this is 44 quarters. So in essence, I'm going to turn this in, or want to turn this into dollar bills. So this 25, I want to turn it into 100, the equivalent of 100 pennies, I would guess you would say, for $1. So basically, what I did is I multiplied this by 4. So I'm going to divide this by 4. If I had 44 quarters, that would be the same as having 11 $1 bills. And if I take 11 times 100, this is 1100. Or if I were working again in money or thinking about it that way, I would have $11. All right, let's do a couple with division next. Breaking up the dividend. All right, this number is 6,318. It looks kind of messy to work with division, but it's actually quite friendly. The idea of breaking up the dividend is to take the 6,318 and to break it up into something that's each piece of it is easily divisible by 9. So this is like 6,318. Even better, let me write it like this. It's really like a 6,300 plus 18. All right, so if you do this, 9 goes into 63 7 times. This is 700. 9 goes into 18 2 times. So this is 2, and you end up getting 702. One of the things I like about this is because the standard algorithm for this, let me show you. If you do 6318, and a student divides this and they get the 7, and they do the 63. Sometimes they forget to put the 0 up here. Like 9 does not go into 1, so you'd have to put a 0. And a lot of times students will simply forget that. They pull the 18 down altogether and they notice it's just 2, and then they tell me the answer is 72 instead of 702. So we don't want them to forget, let me put this in. What we want them to remember, of course, the 0. And then there's no problems. But this other method actually forces us to remember the zeros because we're actually showing the 63 as a 6300 division instead. Now this works really nicely if you actually have compatible numbers. So taking a look at 425, it's not quite so clean. I can still break it apart, but I have to think about it a little bit differently. I mean, the 25 is perfect. So if I break it apart, the nice break would be to break it apart into 400 and 25. Sorry about that. That shouldn't be 24. Let's get that 25 in there. Okay, great. So we're going to divide that by 5. So 5 goes into 400. Well, 5 goes into 4 8 times. This is 80. Now, I don't know that we even need the division here. Let me not do that. This is mental math. The whole point is we're doing it to go in evenly into something that's nice to work with. And then, of course, 5 goes into 25 5 times. So I have 80 and I have 5, so this is an 85 as a division. That's a really nice one. All right, 2 estimation examples, one for multiplication, one for division that we're going to look at. Computational estimation, this is going to be the front-end estimation. So we saw front-end estimation on an earlier problem. 46 times 5, we multiplied the 40 times the 5, we multiplied the 6 times the 5, and we added the results. All that's, handy-dandy. And we could do front-end multiplication for this too and get the exact answer. We do 300 times 4, 80 times 4, and 6 times 4. But the point of what we're doing here is it's supposed to be estimation. So what do? Well, we are going to do the 300 times 4. And we are going to do the 80 times 4. But what our mind is saying is these numbers are already quite large enough that this is going to be a close enough estimate without multiplying the additional 6 times 4. And in particular, if this were a 4-digit number or a 5-digit number at the beginning, it would become more evident and clear that getting a couple of place values at the beginning is getting me fairly close, at least in terms of the factors of the problem. So 300 times 4 is 1,200. 80 times 4 is 320. And if I combine these together, I get 1,520. Now, of course, it's exactly 24 off because I didn't do the 6 times the 4. But this is an estimate for this particular problem using front-end estimation. Last one, 4,132 divided by 4 using compatible numbers. Again, the idea is to approximate 4,132. Man, it's awfully just close to 4,000. Again, with estimation, your estimation and mine might not be the same. But the goal is to do something where the division or the multiplication is easier to do when you're doing a estimation problem. And this one's pretty close, right? I mean, like I get 1,000. The actual answer that I get is a little bit more than 1,000 later on. I agree with that. But it isn't significantly more. So this is a fairly close estimate for this one right here.